Hello everyone, I am Kyoung-Hee Kim, a professor of architecture at UNC Charlotte. Today, in continuation of building-level and community-level flood resilience, we will continue discussing city-level flood resilience and how we can shape our urban environments to better prepare for and withstand flooding. As urbanization and concrete surface areas continue to expand and face more extreme rainfall and rising sea levels, achieving a truly flood-resilient built environment has become a top priority. This slide illustrates 3 levels of flood resilience: building level, community level, and city level. Effective flood resilience involves action at every scale of the built environment. We have covered building level and community level in the previous videos. Please refer to them for more details on each level's flood resilience strategies. In summary, at the building site level, strategies that integrate nature-based solutions, such as green roofs, pervious site, and subsurface cisterns, reduce the runoff load on drainage infrastructure. At the neighborhood and community levels, sponge zone interventions such as tree trenches, rain gardens, and floodable plazas temporarily hold runoff from multiple building sites. At the city or regional scale, larger flood management networks work together, including constructed wetlands, large retention basins, or sponge zones that can hold and slow runoff. Collectively, these interventions constitute a continuous anti-flooding network, from a single green roof to tree trench systems to a whole fabric of regional flood defenses. Addressing flood management at every scale ensures that the built environment is free of flood hazards through tiered strategies designed to absorb, store, and release excess water to underground water. Now let's look at why the city level for flood resilience is important. Rainwater affects a large area, and only a citywide approach and strategic planning can manage water that flows beyond individual property lines. Moreover, flooding is a complex hydrological process. This multifactorial event happens simultaneously across different scales. First, we have pluvial flooding, which consists of rain-driven street floods. Then there is fluvial flooding, caused by overflowing rivers. And finally, tidal flooding, caused by high tides or storm surges. These combined occurrences demand an integrated response that individual efforts cannot achieve alone and require city-level interventions. City-level resilience planning is crucial for addressing social equity. It ensures that protective measures benefit all neighborhoods, not just a few. Implementing large-scale solutions like municipal sponge areas should match the city's overall density and disaster exposures. At the bottom of the slide, sponge infrastructure across the city can be categorized into surface and subsurface water management. In this approach, the urban area itself acts like a sponge to absorb, store, and gradually release stormwater. On the surface of the urban area, networks of green features such as wetlands, bioswales, and other vegetated areas hold runoff in open view. Below ground, subsurface systems such as storage tanks and expanded drainage networks are installed to hold and transport excess water beneath the city streets and gradually release it to the underground aquifer. This slide illustrates interconnected networks of surface and subsurface flood management systems. These interlinked components work together to enhance flood resilience. They hold floodwater from rushing, uncontrolled runoff throughout the city, which drastically reduces peak flooding and protects urban areas. Over time, they filter and release the water safely. This slide exemplifies 2 strategies for city-level flood management. Surface management systems are shown on the left and subsurface solutions on the right. Cities like Bishan have woven wetlands into public parks to absorb excess water rather than simply letting it run off. During heavy rains, those ponds fill up with rainwater, holding excess water that would otherwise flood the streets. As the water slowly drains away, the park returns to its normal use. These anti-flood strategies turn potential floods into manageable events and at the same time provide the city with greener public spaces. In Hebei City, honeycomb modular reservoir systems were constructed beneath public plazas to capture stormwater. These kinds of subsurface networks are invisible in daily life, but during storms they become vital by catching and storing water behind the scenes to prevent surface flooding. Qunli Stormwater Park in Harbin, China, transforms a former wetland into a sponge that protects a new urban district from floods. This 34-hectare park is a pioneering constructed wetland for city flood resilience. Instead of using massive underground concrete infrastructure, the park's natural wetlands retain a large volume of stormwater, effectively protecting the new development from flooding. The retained rainwater percolates slowly and replenishes underground water, while fostering the wetland habitat as a public amenity. This project is an example of harmonizing natural habitat and human interactions. The public trail and elevated walkways at varying heights constantly promote physical experience and visual connection throughout the day and year. It features a ring of retention ponds and vegetated mounds, which together collect, filter, and store stormwater from the surrounding new development area. The project demonstrates multiple benefits: flood control, water filtration, aquifer recharge, biodiversity preservation, and recreation access, all in one design. The success of Qunli Wetland Park serves as a replicable model for global cities pursuing sustainable resilience. Bishan Kyo Park is another example of nature-based solutions in the middle of Singapore. It replaced a concrete canal with a natural river and floodplain. Over 63 hectares of parkland were redesigned to accommodate the Kalong River's dynamic floodwater flows. An old 2.7-kilometer long straight concrete drain was transformed into a 3-kilometer meandering river with adjacent wetlands and an open floodplain. This natural enhancement expands the river's storm capacity by about 40% and safely absorbs monsoon rains. It also improves biodiversity by 30% by providing an ecologically rich, natural habitat. During intense storms, the sinuous river floods the park's basins instead of city streets, then slowly releases the water downstream. Just a few hours after a downpour, the floodwaters recede, and the park's banks are open for play again. Bishan Kyo Park offers a new vision for blue-green city infrastructure, addressing the multifunctionality of enhancing flood management, as well as ecological value and urban life in the heart of a dense city. This video was supported by UNC Charlotte in collaboration with the US-ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. We appreciate your interest in advancing urban flood resilience through innovative nature-integrated solutions.